50 million years ago, the Indian tectonic plate rammed into Eurasia. The impact buckled the Earth's crust, driving a jagged rock wall into the atmosphere. This collision created a physical extreme that dictates the climate, security, and connectivity of the entire South Asian subcontinent. We can measure the scale of this structure by setting a baseline at 8,000 meters. Above this threshold, we isolate a tight, contiguous cluster of the highest peaks on Earth. Navigating this terrain requires modelizing its two structural extremes, the high-altitude points forming the barrier and the low-altitude gaps serving as conduits through it. The physical layout of this vertical wall effectively governs the geopolitics of the entire region. This infographic is a structured study matrix for students preparing for civil service exams. It catalogs the region's geographical data, bifurcated into two datasets. Table 1 catalogs the peaks, or the barrier. Table 2 catalogs the passes, or the strategic gates. We can extract this data and elevate it from a flat list into a spatial model. Complex geographical distributions are often compressed into sequential mnemonics, allowing for high-density information to be recalled under pressure. Tactical utility depends on the ability to project these individual data points onto a three-dimensional mental map of where they sit in space. To build our model, we will extract the top 10 peaks from the matrix and plot their exact positions. We start at the apex, Mount Everest, or Sagarmatha, located in Nepal at 8,848.86 meters. The secondary anchor is K2, or Godwin-Austen. It sits at 8,611 meters, positioned to the northwest in Pakistan-occupied Kashmir. In Sikkim, we map Kanchenjunga at 8,586 meters, which stands as the highest peak within India's undisputed territory. Three more nodes sit directly on the Nepal-China border: Lhotse, Makalu, and Cho-Oyu. Located entirely within Nepal are Dhaulagiri, Manaslu, and Annapurna I. Finally, we plot Nanga Parbat in POK. This structure serves as the anchor of the Western Himalayas. Plotted together, these nodes form a continuous 8,000-meter shield that separates the subcontinent from the north. While the wall dictates where movement is impossible, strategy focuses on the specific fractures where transit can occur. These fractures are the mountain passes, commonly known as LA. They act as the sole vectors for trade and military movement across the subranges. Looking at the western vectors in Kashmir and Ladakh, we isolate the Pir Panjal range. Here, we plot Zoji La and Banihal Pass. These conduits link Jammu to the Kashmir Valley and onward to Ladakh. Maintaining these conduits require navigating unpaved roads carved directly into sheer cliff faces. In Himachal Pradesh, Shipki La, Rotang, and Baralachala provide movement through the Dalatar and Zanskar ranges. Rotang Pass, at 3,955 meters, connects the Kulu region to the isolated Lahore-Spiti Valley. These western passes operate primarily as internal strategic lifelines, critical for military logistics and the support of high-altitude populations. As we move eastward along the Himalayan arc, the passes shift from internal lifelines to international border crossings. In Sikkim, Nathula and Jalepla cut through the Jalepla range. These passes serve as the primary commercial arteries linking India to China. Because of their commercial transit volume, these choke points feature developed paved roads and militarized infrastructure. In Uttarakhand, the Lipulekh and Mana passes connect to Tibet through the Kuman Himalayas. Lipulekh functions as both a major trade route and a religious vector for the Mansarovar pilgrimage. We complete the matrix with the easternmost vector, Photula, in Arunachal Pradesh. Control over these central and eastern passes dictates economic leverage and the diplomatic posture toward Tibet and China. Let's return to the original infographic and examine the hand-drawn sketch of mountain peaks in the bottom corner. This hand-drawn diagram serves as a flattened spatial model of the mountain ranges, encoding the sequential order of the peaks from Dhaulagiri to Annapurna. When we align these hand-drawn nodes with the topographical data, the sketch expands into a model of the actual Himalayan structure. Mastering this geography means the ability to look at localized data and instantly visualize the cohesive structure of the entire continent. The final piece of the source document is a text box containing two mnemonic acronyms. The first sequence operates as a hierarchical algorithm used to generate the name and rank of each peak. As the sequence runs, each character expands into a peak, highlighting its specific node on our spatial map. The second sequence functions as the command line for the mountain passes. Executing this string expands the characters into the names of the passes, lighting up the active connection vectors across the range. Anchoring these acronyms to a three-dimensional mental map creates a durable spatial model of the entire region. The Himalayas are a physical machine dictating the fate of a continent, and this matrix provides the data necessary to navigate it.